Is it so we can use the gamma?
Sure. So that's this parameter, right?
Ah,
So the rho.
so it will be the covariance of xt and xt minus 1 over the variance of st, is it?
Over the variance of
Xt.
right?
Yeah.
So that's sort of what? It's also the autocorrelation of lag one.
Yeah,
So let's call this phi. Right? So that will be a little bit easier.
yeah.
Alright, so that will be a little bit easier. So we call this autocorrelation of lag one. It is phi hat. Absolute value of phi is smaller than one. So this. Alright, and then we can go. So let me ask an easier question. Right, so let's say we have y equals a plus b x plus u. And then you have observations on x and y. Alright, so you have a sample on this pair t from 1 to t. How would you estimate b? It's a simple regression. You remember the regressions, right?
Cool. It's wrong, it's minus 1, it's wrong y. A là cái regression, OS regression.
Sorry? That's a simple regression.
Yeah, simple standard. So I think it's you said that we want to find the b, right?
Yes.
So b will be equal to the function s x from x minus 1 x from y for the yeah.
A hat, alright, so that's good. So you know that. That will be x prime x minus 1 x prime y. This is OLS.
Yeah.
Okay, so how would you estimate A and B? You should say I use the OLS as a method. So that was the answer, but you are right. This is the OLS estimate. Okay. So what is X?
Matrix of x. The matrix of
Right.
right.
So where X is the design matrix, it has a column of 1.
Yeah. Yeah.
And then x1, x2, up to x. Alright, and then we know matrix of y is y1 up to y. So that is what we have as an array. But because that's a bivariate regression, then the OLS, well, I mean, if you open this and we play around and so on and so forth, then the hat will be summation t from 1 to t, xt minus x bar times yt divided by summation of xt minus x bar
Square.
squared.
Yeah.
This is the covariance of x and y, and this is the variance of x. This is the covariance of y and x, and that's the variance of well, xt and xt minus 1 here are the same. But I mean, if I want to be in line with that, then here I could have written variance of xt minus 1. But that doesn't matter because this is a weakly stage to reverse. Alright. So this is how we estimate the slope coefficient. Alright. And well, of course, you know that when there are two results. I mean, under the OLS assumption, I have these, and I have this sample, bounded fourth moments, and so on and so forth. So the standard OLS, and in the stuff, then you know that we have minus a true parameter, square root of it, times also square root t consistent. Really converging distribution on the normal with mean 0 and variance of b. Right?
Yeah. Variance of b.
Cool. let's say you're given this regression, and then you have some sample, and you want to do hypothesis testing. Just want that you remember hypothesis testing. You want to test whether B is equal to B0 versus B not equal to B0. Okay? And how will you go on? Sorry, these are very simple questions I remember that you should remember from your bachelor in econometrics, but I just want to review them. So how would you go about testing this? What do you do? If you have a sample?
Normally, run using data or
That's true.
yeah, right. Yeah. So
And then what does this
find
say?
it cheap. So let me see.
There's a
We calculate it. The
F
value.
this.
Okay.
F this.
And how do you calculate the p-value? The software does.
We're going to set the z statistic.
That's true. The t is statistic. That's
T.
correct. So maybe more historically correct, the value test. So you use the value test.
Đúng rồi, won't this.
Well, this is Abraham Brown. This he was a very important person in the statistics. So I mean that is sort of the basis. And the T statistic has another history. Right, so if you have the value test, the value test actually says, okay, so do the estimation, subtract the true value, and divide by sigma b hat. Alright, that's the value test. So if the null is true, alright, if the null is correct, then this converges in distribution to normal zero. Yeah. So that's the central limit here. Alright. Central limit theorem tells me this. So if you want to basically test, then you have a distribution and so on and so on. Right? Alright. So here, let me tell you a little bit about this pair of hypotheses. So that is our null hypothesis. This is what we believe to be true. Right? And that's the alternative which could be true if the null is wrong. That's something which we call the alternative hypothesis. So here, well, I mean, if I want to go and then test for this, then as you say, then we go and calculate the p-value. And well, the p-value will be something like this. So p-value, this is a two-sided test, which is unequal. Alright. So p-value will be 2 ones. The CDF of the standard normal. And minus absolute value of the value statistic. Right, so this is something that you probably remember. Right? That's the p-value. Alright. So if the null is true, then the p-value would be some number. But then, well, I mean, of course, when you go test, then you need to fix the type 1 error. So you need a type 1 error, which we call it alpha. What is that? Type 1 error? The definition? That's true. So that's the probability that we wrongly reject the correct one. Yeah, so you're right. So that the null is correct, and we reject. That becomes alpha. And there are conventional values. Right? Conventional values are 1%, 5%, and 10%. That's what we have. And that's the p-value that we actually can calculate, and then we compare it with this alpha, and depending on whether this is smaller or larger than alpha, then you make a decision to reject or sort of accept the null. But maybe more statistically to say that the data supports or doesn't support essentially the null hypothesis. Right? So that's sort of what we have here. Alright. So you also know the size of the test, right? So that is That's important, right? So because whatever, you don't want to reject more often than you would like to. And you don't want to reject less than what you are sort of supposed to. So the size should be, the size of the test should always be alpha, or at most alpha. Right? So that's sort of very important to keep in mind. Well, all right, so that is what we have in here. So I think I don't need to talk about p-value here. So, but that is what we have. All right, so that was a small review here. So let me look at this b hat. So I just want to play around with this b hat a little bit. All right, so a bit scribble it. All right. So, so that is b hat. So b hat is equal to, well, that's some summation on the numerator and then some summation in the denominator. This is x, this is also x, this is y. So let's rewrite that. So this sum that I have here, I want to bring it here. You are happy? Fine with that? And what I want to do is that I want to take this y and put it here. Good? Well, I didn't do anything, I just rewrote it.
Okay.
Now I want to take this and call it W x. That's a weight. That is indeed summation. Right? You are happy with this?
Yeah.
So that's a weighted sum of y. Right? So weighted sum of y. Well, so let's say I wanted to calculate the mean of y. Right? Say I want to calculate y bar. So what is y bar? Y bar is summation t from 1 to t by t 1 over t, right? Well, that's also a weighted sum. Indeed, I can take this in and write it like summation t from 1 to t 1 over t by t. Alright. You're happy with this? That's also a weighted. So that's a weighted average, a weighted sum of y. Alright. But that gives me my bar because the weights are not a function of x. Alright. So simply 1 over t, and then I get the average. Alright. So that's also a weighted sum. And this is also a weighted sum, but the weights are a function of x. And then as such, I get this, which is the slope. Right? So it means that if I change this w, then I get different characteristics of y. So if weights are like so, right, then I get b, where b, well, where this is satisfied. And here we have expected value of y given x is a plus bx, right? So that's sort of with the linear combination, you know, under the exogeneity assumption that we have this. And this b, if I want to estimate, say, this guy, then I need hats. So the estimation of the average of y given x would be a hat, b hat, and they are given by the ways. Alright, so far so good. This b hat is this. And if I want the average, then I take the weights and put them like so. Yeah? So it means if I take different weights, then I get different characteristics of y. Can you think of some other weights for y? Do you know other estimators? Something else? Can I change it? I don't like them. They are ugly. I want to change them. course I can. I can think of some other way to escape, whatever. Right? So I want to take you a little bit away from linearities and so on and so forth. Actually, I want to tell you that. So here what we have, right, so remember I wrote an expected value under Euler's assumptions. Under Euler's assumptions. Then we have, say, under Euler's assumptions. Right, so we have expected value of y given xt to be a plus bx. If this model is true, right? So if the model is true, then we have this. Right? So that the expected value of y given x is indeed a plus bx. But that's actually too much of an assumption, right? So let's say I give you two sets of data, all right? So y and x, all right? So some observations, y and x, all right? And I want to know the relationship between y and x, right? So to speak. But let me write there. All right, so that's. So let's say we have observations on y, t, and x, t from y, so in real world, right? Theory, but reality, right? So you observe y and you observe x, and you want to know how x and y are related. Well, one approach is to say, I assume, it's very important, I assume that the relationship is linear. Alright, so that's an assumption. Alright. And y is equal to a plus bx plus some unobserved component we don't know. Alright. But that is something we have. And then we make further assumptions. We say expected value of u given x is 0. Oh, okay. And then bounded moments and so on and so forth. But maybe it's very important to remember that here we assume that the relationship is linear, right? That the expected value of y given x is a plus bx. That's an assumption that we have to check, all right? But of course you know how to check whether the relationship is linear or not. Right?
LM test, LR test.
Exactly, so we basically can use an LM test or the Ramsey reset
Yeah,
test
Ramsey
to
reset.
check exactly whether we have nonlinearities. You know, so oftentimes we don't, specifically in finite and sort of other setups. Maybe it makes sense to say that y is actually a function of x. Right? That's sort of a little bit better. So we go a little bit, not always better, but could be better. That you sort of deviate from this and then come to some other function. And then we don't know this function. Right? Let's say we don't know it. This is something which we call it a parametric model. All right? Because we have parameterized the relationship between y and x. Here we have, well, that's an additive term, all right? So additive in the model, but then here we don't know m. So m is all of the possible functions you can think of, all right? So we don't parameterize it. We don't say what it is. We don't say it's a plus bx or a plus bx plus cx squared. That's also parametric, all right? So this is something which we call it a non-parametric. So y is a function of x. How do I get m?
I don't know.
Maybe we should look around and find it. All right. Well, we still need some assumptions. All right. Maybe let's just stay with this. The expected value of u given x is 0. All right. Well, that's the exogeneity assumption. All right. before you were saying that the covariance of u and x is u, right? So we have these twos. So either this or the other. Which is better? Which do you prefer?
先做 link theorem 是可以。
What is the difference? You have seen them, definitely. Okay. Which one is the stronger?
I think the first one is stronger because we can use that to conclude the two. We can make the other.
That's right. So this implies that.
Yeah.
That's a stronger assumption. This doesn't imply that.
Yeah.
Right, so this is a stronger. Okay. Now the thing is that so this sort of says a negative one. U and x are not linearly related. Well, that's a measure of linear association between u and x, and then we say that u and x are not linearly related. That is what it says. But this says that the average of u, given whatever value of x, is zero. So, but I mean that's sort of something which is very interesting, which actually says that the expected, well, if I assume that, the expected value of u given x squared is also zero. Because, right, so here I'm saying that the average of u given x, whatever it is zero. For example, let's say x is 2, right, or 4. So here when x squared is 4, it is like 2. Yeah. So indeed, I mean, sort of, if I assume that, all right, so if you can work with this, then you can indeed run the regression with adding cx squared. You're going to add x squared 2 with the first, the stronger assumption, as you said, right?
Yes.
I had to cheat to look at them. But I didn't remember your names last time. So if you assume this, then you can, well, include powers, logarithm, 1 over x, blah, 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 anything. But not with the covariance. Alright? Not with the covariance, is just linear association of u and x. So here we stay with the stronger one. Alright? You can't go with the weaker. Alright? Because this m is any function. Alright? And I want the expected value of u given x to be 0, so that the expected value of u given any function of x. Sorry, I'm happy you are not mathematicians, so I can be on the intuitive side. Indeed, we need some restrictions on this answer. It's not any n, but I mean, for any basically functional form, then this indeed will work. Right? So we have to stay with that. And then let's basically go on with m of x. All right. So then how can we actually find this? Yeah. So let's go back to this here that I was playing around with the weighting scheme, right? So if I was choosing the weights like so, then I was getting b hat. If I was choosing the weights like so, 1 over t, then I was getting y bar. Right? Now the y bar is, well, if I regress y on a constant plus u, then y bar will be c hat. Right? So you remember, right? So that's sort of what if you don't have any x, then the weighting scheme would be t. 1 over t. Alright? So it looks like maybe I can indeed choose this weight somehow so that I could get that value, that n. Alright? Well, sort of staying in this framework, I'm generalizing this linear function, this linear estimator, to something which is a little bit more general. Okay? So indeed, m hat at any value x should be summation of some specific weighting scheme at x, which is also a function of all of the observations that you have, times 1. Alright. Should be somehow something like so. So let's maybe value of x, alright? So the Wettinger scheme should be a function of this x and all of the observations. x1, x2, x1, x2, up to xt times 1. T runs from 1 to t. Right? Well, I mean, that W that I wrote there, well, it is indeed a function of all of the x's. It's a function of, because there is x bar here. x1, x2, x3, all of them are here. So that W and xt. So here I have xt minus x bar divided by that sum. And this is indeed a function of all of the observations. So where is this guy? At the value x, then I need to find the value of w depending on the observations and the value of x as I have. Right? So I just need to go like so. Right? So we want to find this w somehow. Okay? So I will come back to this soon. Maybe tomorrow. These are new, right? Is this new for you?
Yes.
And I have to be sure. So keep that in mind. And now a question. What is the histogram?
It's a quite good. It's a quite so you can see it's like a group of data.
Yes. Very good. So let's actually do a histogram here. How many phones did you have ever? Phone?
Now or like
From the beginning, how many did you break with a hammer?
I would say it's like 7.
How many? Five?
Thầy nói gì ạ?
Also five.
Cái gì ạ?
Four.
Hạt rớt á.
Maybe or
Bao nhiêu một giờ hả? Bao nhiêu một giờ hả? Bao nhiêu một ngày?
one.
Broken mobile phone.
How many phones did you have?
In my life, so until now, maybe yeah, 4.
Like 6.
I didn't break any phone. Here, it's I can't get. There's three histogram also, right? That's very few data points. I can't do histogram. But then, so here I have 2 4s, 2 5s, 2 6, and 1 7, right? So I can actually go on. It's saying, okay, so we have 4, 5, 6, 7. So 4 we have 2. 1, 2. Right, so that's a bar like so. 5 we also have 2. 1, 2. 6 we have also 2. And 7 we have 2. But that's a frequency, as we said, right? So here we have beams. Alright, and then in these bins, then we put how many observations we have. Right, so because there are few, then we actually have this all of the distinct values. But oftentimes we have more, alright? More than 7. We have thousands of data. We can actually put them over here, so it will be very obvious. So what we do is that we define bins. Right? And then the bins are, well, I mean, histogram, for example, may look like, so you sort of break this into different pieces, right? So sort of define a mesh. be indeed half. Alright. So, well, I mean, that sort of is supposed to approximate the distribution function of the variance. There's also some smooth curve, which is on the background, right, that you can estimate it using the histogram, right? Yeah. So this is also a non-parametric method, alright, because we don't have the curve. The curve is a function, the f of x, which we don't know. So we use the histogram to estimate. Alright. But the histogram is what I want to do then. So I want to take the idea of the histogram to estimate the m. Alright, that's sort of what I want to do. So, well, indeed, that guy is nothing new. You have had it already. I will generalize it. Alright, using these weights and so on and so forth. Correct? So, now let me sort of check what is the, I mean, how the histogram actually comes about, how it is made, alright? How do you decide that a certain observation should be this big? How do you decide? Well, let me just give your values. For example, let's say 1, 2, 3, 4, 5, 6, 7, 8. So these are the biggies that we have. And then between 1 and 2, then we have some percentage of data. Between 3 and 4, there's some percentage, and so on and so forth, right? And then let me give you a number, and then you tell me in which bin it belongs, to which bin it belongs. Let's say we have a value of 5.5. Where is it going to?
Intrinsic.
It is here, right? How do you know? That's true. So you have a check. We have a checking system. It is in this bin, yes. Right? Why doesn't it go in this bin? Because it's irrelevant for this bin. Right? Right. So if I have a lot of observations, xt, then how will you decide which of them go between 5 and 6? Observations. So you check one by one. Is x1 between 5 and 6? Yes. Then you count. Is it between 5 and 6, the next one? No. Then you don't count. Is it between, and so on and so forth. You check one by one, count them, and then divide by the number of observations, and you have the fraction. Right? You agree. Alright? So let's actually focus on this bin. Right? And I want to calculate the fraction of data points which are between 5 and 6. Alright? So that's sort of the height of this bin. I want to calculate the height of this bin from the observations. That's a fraction. That is 1 over t, summation, t from 1 to t. Alright? Now I need a check for each x. And the check could be is xt between 5 and 6. Right, so that's sort of, well, if it is, that's a 0, 1. If it is, then you have a 1. If it is not, then you have a 0. Right? So this could be a 0, 1. It's a check function. Right? So this check function for this bin, let's write it mathematically. So it will be 1 over t summation, t from 1 to t, an indicator function, alright, which is sort of checking whether xt is between 6 and 5. Well, that's an indicator function, and this will be 1 if xt is between 5 and 6, and it is 0 if not. And then I get the fraction. Alright. You agree? That's how, well, this is how Python, HyperStat, or any other software actually does the calculations. Just checks how many are in this bin, how many are in the other bin, and so on and so forth. All right. Now I want that you pay attention to this. That so I asked you why this doesn't go between 7 and 8, because it's irrelevant. It is not here, it is here. You know, so it goes there. So some data points are relevant here, alright? Some data points are not relevant. So they become zero, the weights. This is weight. 0, 1. It's also weight scheme, alright? So to speak, some of the observations are relevant from point B, some are not. Right. Now let's actually look at this from in a regression framework. All right. Let's say we have some data. We just draw something here. All right. So that's sort of the data that we have. Good. And then the true function that we have is something like so. Well, that's a linear, not really linear. That's a relationship of y and x. So y is a function of x. Well, so to speak, I have y equals, right? So the true one is m of x, and m is the blue one. Right? So the blue one is the function. Okay? And well, that's sort of what we have. So let's say I want the value of m at a certain value here. Right? So I want to know how high m, the blue one, is at x star. Okay? Right. Good. So which observations are relevant here? All. Alright, so if I want to understand m at x star, then I need what? I want to know the whole curve. But it looks like that, let's actually, I'm interested in this height. Alright? So let's actually do the following. Let's look at only these points. I don't look at all, but I look at those and take an average of the black dots. So in this very small region, then I will get m. Alright, so I will give those 0 weight, and this I will give a weight of 1. Alright, and so to speak, so m hat at x star, alright, well, that's one estimate. I can actually say 1 over t summation of yt times, well, I mean, this is the blue one, times, so let's write different, so this is y is 1 over t, summation t from 1 to capital T, yt times some weights. Alright, so these weights. And the weights actually take a value of 1 whenever you are here, and then they take a value of 0 whenever you are out. That will be essentially the average, sort of the value of y when we have essentially, and then well, not divided by t, right? Rather, let's call it t star. Alright. And t star is all of the observations which we have here. Right? So that will be the average, the local average of y. At each point, then we define a small region, and then count, okay, or look at, well, is y close, is x close to x star? Alright? If the value of x is close to x star, then you take the average of the corresponding y's. Right? Then you get a point which is very close to the value of m at x star. Right? You understand? Right. So then I can actually go to all of the other points. And then, let's say I go here, and I move a little. Right? And then calculate again averages. And then go a little bit more. And so on and so forth. Point by point, I get this m. Right? Now the question is, how big should this be? Should it be big from the beginning to the end? Or if I take it actually from the beginning to the end, then I will always get the average. Right? If I get it small, right? But actually I like it that it's, because if it is big, then I will have more observations, right? Because it sort of averages, and you know from the statistics that the more the observations, the better the estimate. Right? But actually here I'm telling you, hey, we want a local average. So you can't actually go too big. stay small, alright? You have to stay close. Well, how many points would you use here? 2, 10, 5, yeah, 20. Alright, I don't know. Okay, alright. Maybe 10 actually. I have some glue, but this is a method which we call it K, nearest neighbor. Sometimes people also write it K and N. Alright, so K is the number of the nearest neighbors, would be 5, 10, 20, something. Alright. And so on and so forth, right? Now, I mean, there is actually something not nice about this K-nearest neighbor, right? Because when you do the estimation, right, then something like so will actually, well, that will be something like that. So that will be averages, right? Right, so you will get essentially averages here and there. So that's a jagged function. You don't get a smooth function. Alright. So because this is, I mean, like, remember, so this is jagged. Alright. So this is also K nearest neighbor. Right? But the neighborhood is actually defined based on the bin. You fix the bin, and then you know how many observations you should count in there. Alright. Essentially, the histogram is jumping. Right? That's the reason. There's a logical reason why histogram is jumping, because you simply count this bin, and then you go to the other one and count again, and it's sort of a step by step, you go up and down. Alright? Now this K-nearest neighbor also seems like so. Right? Because the weighting scheme is a 0, 1. So it's a jumping function, so you get a jumping average. Right? So that may not be actually a very nice way of smooth function. I want to have something solved. Right? So not something which is jagged and so on and so forth. So what do? How do we actually get a soft function? Maybe we change the weighting function. If instead of using a 0, 1, then let's say, well, I mean, we use some weighting scheme which is also smooth, soft. If it is soft, then you also get a soft function out. Right? So I'm giving you the intuition, and later we do the theory. Okay? So you have to sort of establish that this is consistent and so on and so forth. So we also do all right. We'll do them all in Python. So let's do the following. All right. So points which are here close to these actually get a weight of 1. Right? So in the K-nearest neighbor. And then points that are far, they get a weight of 0. All right? But what we can actually say is that, well, let's actually, the points which are very close, let them take a weight of 1. All right? And the further away you go, then you get a smaller weight. All right? For example, let's say we take a weighting function which is like so. All right? So here it is 1, and then you go away, then it becomes smaller and smaller. But so to speak, the point that is here is also somehow relevant for that, because that's part of this function, but not so much. So it gets a smaller weight, right? So it's very small, so 10 to the power minus 5. And then the point which is here then gets a weight of 10 to the power minus 10. All right? So smoothly actually goes. Or maybe you can actually have a function which is like so. All right, so a triangular function. In the well, at x star, then you get a weight of 1, and then the further away you go, then you get indeed 0, or so smaller and smaller. But this is something which we call it a kernel. A kernel. All right, so that's a kernel function. All right, so this is called a triangular kernel or a Palaschnikov kernel. This is can you give it a name? What form does it have?
Yeah.
Exactly, that's the Gaussian kernel. Okay, that's Gaussian kernel, this is a punishable kernel. There are many more. Yeah, but that's enough for us, okay? So that's a punishable or triangular kernel, this is the Gaussian kernel. And how does it actually work? Alright, so I want to basically give some weighting scheme to all of those values. Alright, that's sort of what I want to do. Well, I mean, the weights should also sum up to 1. Alright, well, so that you have a proper weight. Yeah, so sort of weighted sums. The weights should sum up to 1. But they are perched on something, some kernel which we call it, say, Gaussian or whatever. Alright. So I'm going back to here. When k-nearest neighbor, I told you, there are a few numbers close to this that you calculate, take averages and then go on, or you can also take some other values. Good. This turn has to be. All right. So now I'm going to the assignment. All right. Well, I mean, this kernel estimator for M has a name. Well, these are, I told you a lot of names. Chebyshev and Markov and whatnot. Jensen you brought here. In our class. This is called Nadaraya Watson. This is the name. All right, Nadaraya Watson. So this N W. Right? Nadaraya Watson. Two people. They were humans. All right, and the Nadaraya Watson estimator looks like so. All right. So this is Y. Alright. This is the kernel for all of the observations at X. Alright. And then divided by the summation of the kernel so that you have the sum of, well, I mean, this is like a weighted sum. For example, you have summation of W1, Y1, plus W2, Y2. W3, Y3, Wn, Yn, divided by summation of the weights. So that becomes a weighted sum such that the first weight is W1 divided by the sum of the W. W2 divided by the sum of the W. W3 divided by the sum. So that the summation of the weights is 1. So the denominator is simply a normalization. The numerator is what I just told you. That you take a weight which is very large when you are close to the X star, and then becomes smaller and smaller, basically slow to 0. Right? So it sort of vanishes and becomes smaller and smaller. Should we do a little programming with this? Then you get a curve, and then you do an estimation. Yes. Maybe there will be a bit of fun. I don't know, I mean, how much should I go with the showing and so on and so forth, because it seems like you are very fluent with the theory. It's sort of very easy to follow. Maybe I should make it somehow not too big. So that we can understand each other. So let me see, what should I do? minimization. Right. I mean, before actually I go on here, there is something which is important that I mentioned. Look, here we have an H. H is called the bandwidth. Right? So K nearest neighbor that we had here was, it's not actually bandwidth, but it also tells us how close you should be to that point. And Watson also has some measure which controls how close you are, measure of closeness. Right? And that is called H. Right? Indeed, H is the length of, well, this is say 2H. So so here we have a band. Right? So here, well, that's a band around 1x. Right? And this band is 2H in another 2 times H. That's a real number. Alright? And that shows up here in this formula. Alright? So, well, of course, you would like that H is small. Right? So if H is small, then you're going to have, well, you will be very close to the M at X star. You don't actually use too many observations, too many irrelevant observations. And indeed, you wish this H to go to 0 as symptomatic. The smaller and smaller. Like, I mean, so here, I would be, so if I have many observations, I will make these bands smaller and smaller. So the beams, so have more beams, and that will be softer, right? In the histogram setting. And that's the same here. So, well, the idea is the same. I like the fact that these are averages, weighted sums. That's also weighted sum, right? But the weights come from, well, they are depending on x, well, with this weighted scheme. Right? So that is this H. And we wish this to be smaller and smaller. When this is small, then this becomes big. Right? So it means that this curve will become like so. Right? That the weights actually, depending on age, actually become softer and they seem to include more or sort of less observations with more focus on these points, essentially. Right? If H is large, then you will have more observations. Right? So in each bay. So you will have a better average, a more matching average. Right? Sorry, if H is bigger, then you will have more irrelevant data points. So you will have a bigger bias, but you will have a smaller variance because you have more observations. Right? If H is a small, then the bias becomes smaller because you have more relevant data or fewer observations. So the variance becomes bigger. Right? You understand? So, yes. So if you have more observations, you don't say to this, you know, it's not equal. It's you have.
Not all of us have that.
No, not everybody. But it's not equal. It is equal. When somebody sneezes and then I say this.
That's fine, yeah.
This is one. So, but this is equal. Alright. So just want to sort of stress this. So if H is smaller, then you will have a smaller bias, bigger variance. If H is larger, you will have a bigger bias, a smaller variance. Right? So bigger bias means that you don't hit the function properly. So that sort of not used. Right. But let's actually go on I'm going to do a bit of programming with some functions. Let me, so we'll do a simulation. We'll simulate some data. Then we do some stuff. This review actually became longer than I wanted. But that's okay, I guess. You learn something new. Let's say you have a function which is point times, what did I choose? So let's go that way, that's actually. Let's just start with, let's say the sample to be 200. Alright, so we have sample of 200. Y equals, say, C of X plus some noise. And then let's say noise is 0.3 times U, and U is IID normal 0. So that's the sinus function. And the sinus we actually do in such a way that we have two periods or 200 operations. So to speak, we have something like, well, starting at 0, that's one period, and another. That's the C function. And, well, with some noise, so the observations will be dispersed around. Alright, so this is Y. Okay. So the dots are the observations. Alright. And, well, I mean, in reality, you are given the data, then you want to estimate the linear, well, so the relationship of Y. So that is the task. You want to basically see how this basic function will look like. Well, with some parameters, right? So what we assume expected value of this given X is 0, right? And then we go on with another arrows. What I don't want to find. But it's at least produce some data, so it is good to do. Right. Let's do the following. So if I do something and you don't know what I have, right? So if I use a package and you don't know what it is, you ask me, I will explain. But I know that you have had a Python course, right? So I know that. So let's import NumPy as NP. Right? So that's the beginning. Let's import matplotlib. The 5plot as PLT. And that's enough. Alright, we don't need anything else. Well, I mean, let's actually set the seed of the random generator of NumPy to 0. So that we have the same data. Right, so the same position numbers. Let's say we have the sample size, as I said, is 200. Let's generate X to be line space. Space. But let's say it starts from 0, goes to 10, and then we need t observations. Alright, so that's sort of the from 0 to 10. So it's roughly 2 pi is what? 2 times pi is 28 roughly. So 10 is a bit bigger. So that's a bit more than 2 cycles. 2 pi plus a bit. So let's generate y. So that will be np dot c of x. I could actually use any function. Plus 0.3 so that the variance is in y. I don't want too many variables. So variance will be 0.1, roughly 0.09. Some random variables, np dot random dot ran n, so that it is standard normal of t observations. Okay, so that's my y and that is my x. Let's maybe run this just to see that things are alright. So that is x, that's an array, doesn't have a second dimension, that is y, also doesn't have a second dimension, and you can actually reshape it. Right. Let's have it reshaped to be x dot reshape. Let's give it a -1 and a 1. Alright, so that's the shape. Let's run this. So that will be a 200 by 1, right? Okay. Do we need me on your laptops? Should I move to your laptops if you have problems with writing the codes? I'm asking. If you need me, I will move to you. Yeah? You're fine? You can write this program.
Yes.
That's great. Well, let's actually go on and then do, well, look, I mean, this actually, I wiped another, so here for every x, alright, then we need the estimator. Alright, the estimator which we know. So m and x is summation. T runs from 1 to t. K, well, that's the kernel. xt minus x divided by the bandwidth, which we want, well, you have to basically choose some number for it, times 1t divided by the normalization. Right? So that is what I'm going to do. And for all of the x values that I have to do this, so I need some function that does that for every x. And then put it in there. Right? So we just write a function which does this m of x for me. Alright? So let's define, say, another Watson, right? Watson. And well, that's a function which takes some x values, takes some y values, and then the sample by sort of this guy h. Right? So that is what I got. Alright. Well, the sample size is t, so we are happy with that. Alright. Now, so here I need m for every x. So maybe I just define some value here. Right. And something here, and then I add all of these sort of estimators for 1x. Alright. Let's just stop here. Okay, because time is over. And then once you go home, complete. Alright. So tomorrow you come, and then we do the discussion of this program together. So gonna start from this book. There's non-parametric econometrics by Hakan and Ahmad Ghulam. As in Hakan, Ahmad, he's Australian. I had my course with him.
Wow.
So, I mean, I learned non-parametrics from the guy. It was very important. You have to check if he's active, but I haven't heard from him. So if you Google it, then you find the PDF of the, or you can read non-parametrics. Alright? But you actually, well, there's a lot of theory and so on and so forth there, and card fitting, and so on and so forth. How to get derivatives, because sort of they're interesting too. I'll tell you maybe a little bit about the derivatives next session. I can't tell you what over the years, but you can read a bit more there. Your task is to program this to get the curve. Then do some plotting so you see how it works. For H, maybe I should tell you how to choose H. Well, choose H to be, say, 10, 5, and 15. Choose, with 5, you generate some curve. With 15, you generate some curve. With 10, you generate some